So now we're going to be talking about the concept of angular momentum. So as a rigid body is impelled to move by a net resultant moment, it will naturally have momentum. As an object with mass moving with a certain velocity, it will have a value for its linear momentum. However, if it's spinning around in a circle, it will have what's known as angular momentum. So it's essentially how much it can resist changes in its angular velocity or angular acceleration. So it's essentially linear momentum times the radius at which it's acting. We denote it by the letter L, and it's mv or, which is equal to p or, where p is linear momentum. Now, the way in which we can link linear momentum with more rotational stuff is with this thing called a moment of inertia. So the moment of inertia is slightly different to a regular moment. We know that for a point mass rotating in a circular path, the angular velocity is the change in angle over time. But for a rigid body, the moment of inertia is a quantity which tells us the value for omega, which causes an angular momentum of L to occur. So I is a constant for your shape, and as either the angular momentum or the angular speed changes, the other one will change with it. So it's written, the moment of inertia is the angular momentum divided by the angular speed, which can also be written in sort of a form as L equals I omega. Now this is sort of like F equals ma in a sense, kind of like this, but this quantity shares one of its inner quantities with the moment of inertia, that being one of the meters. So it's still kilogram meters squared per second, which is also this, but it's missing a factor of a per second. But this is the similar law that's used for rotating objects, specifically rotating rigid objects. The moment of inertia is different for certain objects. For instance, point masses. So we can actually do moments of inertia with point masses, even though it seems counterintuitive. But for a standard point mass in rotation, we have to use a specific formula for I. So it varies depending on the construction of the object. So it also depends on where it's rotating through. So the moment of inertia of a cylinder rotating about an endpoint, so rotating, say, like this, is not actually the same as, say, an identical cylinder, but this time rotating about its center of mass, sort of spinning this way. Or even spinning around this way. So the moment of inertia is different for that. For a point mass, the moment of inertia is m or squared, where or is the radius of rotation and m is mass, rather obviously. We can also show that any compound object, if it were to be crushed into a point mass with the moment of inertia consistent throughout, so the moment of inertia doesn't change, it would actually inhibit behaviors of a point mass, even though it technically isn't and shouldn't be considered as such. The radius at which this needs to happen with is known as the radius of gyration. We won't be going more into the radius of gyration, but it's essentially just a fairly common thing that comes up in definition sort of things. So, what about different moments of inertia for objects? Well, here are a couple ones. So if you have a uniform rod of mass m and length 2L about the midpoint, the moment of inertia is 1/3 ml squared. A uniform rectangular lamina of mass m, length 2L and width 2K about an axis through its center, so anywhere through the center, it can be rotating this way or this way, is 1/3 ml squared, much like the uniform rod about the midpoint. A uniform circular disc of mass m and radius or about its center is a 1/2 m or squared, and a point mass about a radius or is m or squared. Now, another key one to note that I didn't include is for a sphere, the moment of inertia is 2/5 m or squared. So that's pretty much all you need to know about the moments of inertia.